In this tutorial, we will learn how to estimate a market pay line using R. So you should have RStudio open. Be sure to go to File, New File, RScript to open up your RScript editor, or in other words, your RScript file once you save it. I'm going to go use the hashtag and make a quick note describing what this tutorial is about, and it is about estimating a market pay line in R. And so before we get started with the actual estimation process, let's make sure that we set our working directory and specify where our data are saved. And so I will use the setwd function from base R, and in quotation marks, I'll note that the data for this tutorial are saved in my H drive R workshop folder, and I will run that selected line of script there. Now, alternatively, you could go to Session, Set Working Directory, Choose Directory if you wanted to do this via dropdowns. The next thing that we need to do is read in the data that should be located in our working directory folder that we just specified. Now, if you haven't already, make sure that you install the reader package. That's reader, R-E-A-D-R, all lowercase. I have recently installed it and updated it, so I don't need to run this first line here, but you may need to do that. You will definitely need to run this line, which is library function, as the sole parenthetical argument. Enter the name of the reader package here, as you can see, and run that line of script. Now that means we can access the read_CSV function to read in our data from our working directory, and because we have accessed that reader package. And so let's name this data frame object that we're about to read in the data for and assign the data to this data frame object. Let's call it MP for, let's say, market pay. And this is lowercase m, lowercase p. We use the left-handed arrow to assign the values of the data frame to this object here. So we will use that read_CSV function. And in the parentheses and within quotation marks, we'll type in the exact name of the data file as it's saved in our working directory folder, which is marketpay_line.csv. Note that the M in market is capitalized, the P in pay is capitalized, and the L in line is capitalized. And let's click run. Okay, so as you can see, it's successfully read in here. Let's take a look at our data by going to our global environment and clicking on the name of our data frame object we just named, which was MP. And so here you'll see that we have 5 fields or variables. We have the job family field or variable, which has OA and NU as the 2 categorical responses. So this is a nominal variable here. And so let's assume that OA stands for office job family, NU stands for nursing job family or nurse job family. And then we have the unique identifiers under job ID for each one of these benchmark jobs. And here are the job titles for these benchmark jobs. In total, we have 25 jobs from 2 job families here. And note that we also have the final 2 variables are points and pay. Points stands for the job evaluation points. Let's assume that they did some type of point factor system or point factor method to derive these points for each job, benchmark job here, by using compensable factors and scaling and weighting and so forth. Now the pay is the market pay, and so this comes from market survey data. Let's assume that it's already been aged and it's already been weighted, and that this is the final estimate here for, let's say, the median market pay here, that we're going to use as our reference point. So what we're trying to do here is we're ultimately going to regress pay onto points because we're trying to see how well our internal job structure, as represented by the job evaluation points, reflects what jobs are worth in the external environment or the external market. Okay, so the next thing that we're going to do is let's visualize the association. So the association specifically between points and pay. And so to do so, we're going to create a scatterplot, and we'll use a function that comes from base R, meaning we don't need any specific package to use it because it comes default in R when you download it. And so it's plot with a lowercase p. And the first thing we'll do is we'll note the name of our data frame object, which is MP, add a $, and then the name of our predictor variable, which is points with a capital P. And then note that we have data frame again, $, and then pay, which is our outcome variable. So here, as the first 2 arguments, we've entered what is ultimately going to be our predictor variable and our outcome variable. Now, as the third argument, this is optional, but I'm going to add a more meaningful label to the x-axis, and let's call it job evaluation points, because note that the x-axis will correspond to the first variable that we entered here, which was points. Now I'm going to add a fourth argument here. This is also optional, and this is going to be the y-axis label. I'm going to call this market pay, and I'm going to put a note in here that this is in dollars, and we'll just assume that implies US dollars. Okay, so the next thing that we want to do is let's run this function here. Okay, so you'll see here that we have a scatter plot where we have the job evaluation points here on the x-axis, market pay on the y-axis, so points versus pay. And so each of these little dots or circles here represents a unique job here, okay? And so what you can start to see here is that, yeah, there's some linearity to this association, but there might also be some curvature here too, and meaning there might be a nonlinear association. So right off the bat, we'll probably know that we need to estimate both a linear model using simple linear regression as well as a polynomial regression model in order to estimate this curvature. It looks like there's a single bend or curve here in this association, which would suggest a quadratic functional form. Or in other words, quadratic would be squared functional form. You could think of this as being exponential growth here. Okay, so now we are ready let's start with a simple linear regression model. So let's evaluate the statistical assumptions for a simple linear regression model. Now, with a simple linear regression model, there's another tutorial called Simple Linear Regression in R. If you want more background information about statistical assumptions and just running a simple linear regression model in general, do check out that tutorial. I'm going to move rather quickly through this, assuming that you've already covered that tutorial here or prior to this point. Okay, so the first thing that we're going to do is actually prior to evaluating the statistical assumptions is we need to actually specify our model so then we can actually estimate those statistical assumption diagnostics. So I'm adding a hashtag here above as a note. Let's specify our SLR model, which I'll just make a note that this is simple linear regression. So SLR is what we'll use as the abbreviation. And to do so, we're going to specify our model using the LM function, which comes from base R. It's the linear model function. And we're going to use this particular function because it's more flexible and it can be used more easily in additional functions, and we can name objects and create objects based off of it with greater facility than perhaps some other linear modeling functions we might use, such as from lessR and its regression or regbrief functions. So first we need to come up with a name for our regression model. Let's call it reg_all, meaning we're going to use all the data here. And that's a whole other tangent that we're not going to really get in here. But notice that there are two job families. There could be different geographic regions. There's a whole number of reasons why you might not use all the data to estimate a market pay line and why you might actually have separate market pay lines depending on job families, geographic location, and so forth. We're not going to get into that in this tutorial. We're just going to assume that we're using all the available data from those two job families, and let's assume these are all jobs from a hospital. Okay? All right, so let's name this model reg.all, and we will use the left-handed arrow to assign our model to this. And so we're going to use that LM function, linear model function from base R. And the first argument is to specify our regression model or regression equation, which is going to be pay regressed on points. Now notice that we have, undo that. Notice that we have a tilde symbol here, so it's that squiggle line. And so to the left of the tilde, we have our outcome variable, and to the right of our tilde, we have our predictor variable. So it says pay is regressed on points here. Now as our second argument, we are going to add data equals in the name of the data frame, which is MP, which is what we named our data frame as up here. And this is where these two variables come from. Okay, so let's go ahead and click run there. Now note that you don't get any output here other than noting that the model ran, because we're not actually summarizing the model yet. We've just created this object, which we're now going to plug into different diagnostic tools for evaluating statistical assumptions. So, okay, now we're ready to evaluate those statistical assumptions. And one of the first things that we're going to do is we're going to look at a plot of the fitted values and residuals. Okay, and this will help us test the assumptions of whether or not the residuals are equal across observations, whether the average residual error is about 0, and whether or not there seems to be any evidence of a departure from linearity. Okay, so to do this, we'll actually use that same plot function again we used as above from base R. And this time, however, we are going to enter the exact name of that regression model we created up here, which is reg.all. That's our first argument. Our second argument is just the numeral 1. So there's 4 possible plots that are associated with using a linear model regression like this, 1, 2, 3, 4. And to reference the first plot, which happens to be associated with a scatter plot of the fitted values in relation to the residuals, we'll just note 1 here. So watch what happens when we run this. Okay, so here we get that scatter plot. And you can see we have the fitted values on the x-axis in relation to the residuals. So the fitted values, this is another way of saying predicted values here based on our model, given the predictor values that we plug into the model that are the actual observed ones. And the residuals is any error in prediction here. And so what you can see here is that there's some pretty clear curvature. And so this seems to be suggesting that there is some non-linearity to the data here. Another thing that you'll notice too is that the residuals don't seem to be equal across the distribution. Rather, they seem to actually grow larger in the middle of the distribution, perhaps. And the other thing that you'll notice too is that, or rather, the residuals are actually greater on the tails here, and that the average level is probably greater than 0 if you look here. So we've have some reason to believe that we may be in violation of at least a few of those statistical assumptions, namely that the residuals are not equal perhaps across levels of the observed values, and that the average residual error appears to be greater than 0 as opposed to 0, which is what we'd be looking for, and there does appear to be that departure from linearity here. Okay, and another thing, if we looked back at our last plot, we don't necessarily see that bivariate normal distribution here that would also be an assumption of linear regression because there does appear to be some curvature there. Okay, so the next thing that we're going to do is we are going to create a normal QQ plot, and this is a way of looking at whether or not the residuals are normally distributed, which is another assumption of simple linear regression. And we're just going to grab the same script from above, except we're just going to change the 1 to a 2, and this will request the second plot here, okay? And so click run there. Okay, so what we would like to see is along this dashed line here, we would like to see that all these points fall along, and these are all the individual cases, all 25 cases here, or jobs in this case, that they all fall along this dashed line because that would indicate that we have met the assumption of a normally distributed residuals, okay? And so these are the standardized residuals here, and you can see that we have some departures there on either end, but this actually doesn't look too bad here, okay? We do have some departures on the tail, but in general, a lot of them fall pretty close to the line. So let's say that in terms of the normality of residuals, we're doing pretty well here, okay? All right, so the next thing that we're going to do is we're going to estimate, make that a capital C because this is someone's names, Cook's distance values, okay? And Cook's distance values are commonly used as indicators of outlier, or can potentially flag potential outliers or influential cases in our data. Because that's another assumption of simple linear regression, is that our data are free of bivariate outliers here. Okay, so the way that we're going to request this is by using that same plot function again, okay? Except this time we're going to request the fourth plot, so type 4, and it's just the same argument as before, and click run. Okay, so now we have all the cases here, which they call the observation numbers, which are associated with the row numbers in our data frame. So you can see rows 1 through 25 here noted. And anything with a numeral on it indicates something that's potentially flagged as having a high or a normally high Cook's distance value. Now, 25 seems to be the clear winner here. And the question is this of notable size? Should we consider this to be an outlier or an influential case? And bear in mind, we have a pretty small sample size here, only 25 cases. So we're going to be a little bit sensitive to finding these influential cases here. That is, each case is going to carry more weight because we have such a small sample size when it comes to estimate our regression equation or regression model, and specifically in this case, our regression line. Okay, so let's take a closer look at Cook's distance. And to do so, we're actually going to create a new object, and this is going to be a vector, and we're going to call it cooksd just arbitrarily. That's cooksd with a capital D and a lowercase c. And what we're going to do is we are going to use the cooks.distance function from base R. And the cooksDistance function simply takes one argument, which is the name of our regression model, which is reg.all here. So let's run that, which assigns the cooksDistance values to this cooksd object. If you were to just highlight that cooksd object, click run, you just get the vector of all 25 cooksds. Now note they're not in any order, and so that's not going to be as easy to work with. So what we can do instead, or what we can do in addition, is we can actually sort these. And so to do so, we're going to just overwrite the existing cooksd object we just created, and we'll use the sort function from base R, and as the first argument, we'll put the existing cooksd object, and then we will use the decreasing equals argument and true to say that we want these cooksd values in decreasing order. So let's run that. Now let's click on and highlight cooksd, that object, once more, and so now you'll notice that these are in decreasing order here. Now, if you were to have a lot of these, in this case we have more than 25, we can also just look at maybe the top 20 of them to get a good idea of what the top 20 cooksds are. And so you could use the head function from base R, type in the name of the cooksd object you created as the first argument. As a second argument, you could type in, let's say, n equals 20. We could also put n equals 10. The default would be n equals 6 with the head function. Click run. And so here we have the top, in descending order, the top 20 cooksd values. And so what's a problematic cooksd value? Well, there is one rule of thumb that would say that if you take 4 divided by your sample size is going to be a cutoff for cooksd. And so, for instance, if we come down here and we do 4 divided by our sample size of 25, this would say that a cooksd cutoff would be 0.16. So any value that's greater than 0.16 could be a potential outlier or influential case. In this case, we see row number 25, row number 1. These are both cooksdistances above 0.16, so these could be potential candidates for removal, or more specifically for special investigation. So looking into and making sure these data were actually entered correctly. Now there's also another cutoff, which is much more liberal in nature, which is simply is a cooksd that is greater than 1, okay? So the idea behind this is that, again, this is very liberal, and we're using a small sample size. This might be the one we want to go with here. And so here you can see only one of the cooksds is greater than 1, and so that could be a potential candidate for removal. All that said, we have very few cases to work with here, very few observations, in other words, and so I would be hesitant to remove anything, especially given that these are actual job values here. Now, if you were to be including executive pay or something like that, that really throws things off because it's so incomparable to the other values perhaps in the organization, then you might want to remove those and do a separate analysis for executive pay if possible. Okay, so let's assume based on this, we're not going to remove any influential cases or outliers here. This is still pretty close to 1 here, and we might not be as concerned. That said, we're also estimating a linear model here, and so perhaps we'll get better estimates. We would have gotten better estimates if we were to actually address the nonlinearity. So that's one potential issue with going with a cooksd there, or with going with a linear model when apparently there might be some curvature in the association. Okay, so the next thing that we're ready to do, let's assume that, well, it's not great, but we've reasonably satisfied the assumptions, or we've come kind of close to satisfying the assumptions, these statistical assumptions for a simple linear regression model. And so for that reason, let's move forward and interpret the simple linear regression model results. Okay, and I should note that you're never going to perfectly meet these statistical assumptions for any model. It's really a matter of just coming as close as possible, or feeling confident rather, that you are not in egregious violation of these statistical assumptions. Okay. All right. So in order to interpret our our simple linear regression model results, what we're going to do is use the summary function from base R and that name of that regression function we created, which is reg.all, and click run. Come down here to the output. Okay, so let's take a look at what we have here. We have information about the residuals and so forth here. We've already inspected those visually earlier. The coefficients, this is your actual estimated regression model and equation here. We see the intercept value, which we're not usually interested in terms of whether or not it's statistically significant, but it is going to be important when it comes to actually plotting the regression line, assuming that the the coefficient here associated with our predictor variable is statistically significant. And so here we have points. So this would be the regression coefficient associated with the predictor variable points in relation to the outcome variable pay. And we see that the regression estimate is 145.44, and the p-value is less than 0.05, our conventional two-tailed cutoff. And so we would conclude that this unstandardized regression coefficient is statistically significant in this case. And so it's statistically significantly different from 0. So in other words, we can say that points does seem to have a positive association with pay. And specifically, we could say something like, for every additional job evaluation point, the market pay tends to go up by $145.44. Or in other words, every job evaluation point is worth about $145.44. Okay? All right, so the next thing we're going to do is come down to our actual model fit information here. You get your degrees of freedom, all that sort of stuff, your residual standard error. But what we're really interested in here is our unadjusted R-squared value and our adjusted R-squared value and the associated F statistic and the associated model p-value. The p-value here will be exactly the same since we have just a simple linear regression as the p-value associated with the regression coefficient here. Nonetheless, we'll still interpret it. So the unadjusted R-squared value is 0.871, or 87.1% of the variability in pay is explained by points. Now, the adjusted R-squared value it's a more conservative estimate because whereas the unadjusted R-squared value, it describes the sample, the adjusted R-squared value is meant to describe the population from which the sample is drawn with respect to the parameters in the model or the variables in the model. And so it's always going to be a little bit smaller or a lot smaller depending on the data and the number of predictor variables in the model, sample size, and so forth. And so here we see about 86.6% of the variability in the outcome, which is pay, is explained by the predictor variable, which is points. Okay, so these would actually be pretty good. So what are our standard rules of thumb? Well, I've come up with some ones that you might want to use in interpreting this. Now, we're not going to use the standard R-squared values rules of thumbs that perhaps Cohen has offered and so forth. We're instead going to use ones that are specific to this market pay context because this is a very specific context and we expect these models to fit very well. In fact, we expect that the predictor variable is going to be usually explain a lot of variability in the outcome variable. Okay, so we have much higher standards in this regard. So let's talk about the qualitative descriptors. And so I'll just type these out for you. But for something to be, let's say it's an excellent fitting model, let's say that it needs to be in the range of 0.90 to 1. Okay, so in our case, we are shy of that, but we would fall in this range of 0.8 to 0.89, which we'll call great fitting models. Okay, so still really good. But again, you can see the bar is pretty high here for these market pay regression models because, again, we do expect these to fit pretty well here. And the next level would be 0.7 to 0.79. And we'll call these good fitting models here. The next level would be 0.50 to 0.69, and we'll just call these acceptable. So this is kind of the minimally acceptable here. And then below that, we have 0.40 to 0.49, and we'll call this questionable. Okay, so you're kind of in this weird zone here if your R-squared value comes between 0.4 and 0.49. Now, if anything is between 0 and 0.39, let's just go ahead and call that unacceptable in this context. Okay, so these are the qualitative descriptors. So in our case, we could comfortably say that we're doing pretty great here in terms of model fit, plus the F statistic or F value that's associated with this model in the R squared is statistically significant, as you can see here, evidenced by the p-value. So in other words, this model fits the data significantly better than a model that has no predictors in it, which would be a null model here. Okay, so we're doing pretty good. And the next thing would be to, let's actually visualize this simple linear regression model and visualize what is ultimately our market pay line, which is our regression model here, where here's the intercept value and here's the slope for that line. Okay, and so to do that, I'll make a note here that we are going to visualize the SLR model. We are going to use the plot function just as we did above, and let's actually go up here and copy this exact same script we used above here, and then we'll just add on a couple of extra arguments. So what I'm doing here is that if you look back, I'm just going to scroll back through, that we, here the defaults is it just barely kind of squeezes everything in. It tries to make the most efficient use of the space. We're actually going to adapt that a little bit here. And so let's use the y lim or the y-axis limits and the c function from base r to note a two integer vector here. Let's note that we want the x-axis to range from about 300 to, let's say, 1,000. And that's about where it is right here, but just let's clearly specify it. So from 3,000 to, or 300 to 1,000. Now, as our last argument, let's do ylim equals, and let's say that, well, let's actually range this from about 10,000 all the way up to 140,000. Okay, so 10,000, and then the next value is 140,000. Okay, so these arguments, actually all these arguments here, the last four are optional, but they will make for a more, in my opinion, aesthetically pleasing plot. So let's go ahead and run this. I'm going to open this up a bit. Click run. Okay, and so that did work there. And so the next thing that we're going to do, see, we've adjusted the limits here. So now you can see some slight variation there. Okay, so the next thing that we're going to do is we're going to add the actual regression line into it. And so we use a function called AB line from base R. And as the first argument, just enter the name of that regression model we've been using, which is reg.all, as your first argument. And as your second argument, this one's optional, but let's just make this, the default will be a black line, but let's do call equals for color equals. And let's specify the name of a color here at all lowercase, which is red. So we'll make a red line here based on a regression model. And so if you run this next line, it'll superimpose onto your existing plot, it'll superimpose that regression line. So this is actually our regression line here. Okay, so as you can see, we have our regression line plotted here, and you can start to see that, yeah, it's doing a pretty good job. There is some definite linearity. We have a positive association here, and we saw that represented by a really strong R squared, or rather a great R squared value here. But we can see that maybe a nonlinear association, a quadratic functional form with a curve in it here, a single bend, might be a better way to estimate this, okay? And so this brings us to specifying a polynomial regression model, okay? So now we are going to specify a polynomial regression model, and I'll abbreviate that as PRM, polynomial regression model. And by polynomial, it's any time where we start to use exponents and so forth. So this comes from, you might have learned in algebra courses and so forth. And so that's what we're trying to do. And specifically, we're going to add another term to our regression model that's going to be the quadratic or squared term of our predictor variable to help capture some of this curvature here, hopefully. Okay, and we'll see whether or not that actually a nonlinear model fits the data. Okay, and if you have questions on polynomial regression modeling in R, check out, there's an entire tutorial called Polynomial Regression in R in which I go into more detail on how to actually do this. So as before, we need to specify the regression model. Let's name it something new, but something that looks familiar. So let's do reg.all underscore poly this time to note that this is a polynomial regression. And we'll use the left-handed arrow to assign our regression model to this object that we'll call reg.all underscore poly. And we'll use the same linear modeling, the LM function from base R as we did before. To the left of our tilde, we're going to put our outcome variable as we did before, but here's the difference. To the right of the tilde, we're going to use the poly function from base R. Okay, so it's P-O-L-Y, all lowercase, from base R. And within it, we're going to specify two arguments. So the first is going to be the name of our predictor variable, which is points with a capital P. Okay, that should look familiar. And then as a second argument, we're going to enter 2. So 2 means that we have, is that this is the quadratic form. This is a squared term. So it's going to estimate, like we saw before, just the regular points to the first power, which would just be the regular values themselves. But then it's going to add an additional regression term, or a term to our model, which is going to be points squared. Okay, so we'll have our intercept points and points squared. That's what this is doing here. Now, if you added a 3 here, this would create a cubic model, and that would be estimating if we assume that there was 2 bins, where actually there was a change in direction, or the 2 bins in our actual model there. Okay. Now, there's other ways you can estimate a polynomial regression model. And if you'd like to learn more about those, check out the polynomial regression tutorial that I've created. And note what's nice about this polynomial regression, or this poly function here, is that it actually standardizes your variable and centers it. So it's going to address any issues of collinearity and so forth that can actually help with estimating more accurate standard errors. Now, it wouldn't necessarily lead to different results in terms of the overall model fit. Actually, it shouldn't in most cases. But if you're trying to interpret some of the lower order terms in your model, this is something you might consider going with this approach that I'm showing you here. Okay, so the second argument, so we've specified our regression model here, the polynomial regression model specifically. The second argument is going to be data equals and the name of the data frame, which is NP. Okay, this is what we read in at the beginning, and this is where these two variables come from, points and pay. Okay, so let's go ahead and click run there. So as before, we've just specified the model here. The next thing we're going to do is we're going to take a look at some statistical assumptions. Specifically, we'll evaluate statistical assumptions of a polynomial regression model here. Okay, so some of these will actually be the same as with our simple linear regression model. And so we're going to use we're going to estimate the fitted values and the residuals in a scatter plot like we did before, and we'll use the exact same script with the exception that we're changing the name of the regression model here. So we'll do reg.all_poly, and as our first argument, second argument, the numeral 1 to request the first plot, which is going to give us that scatter plot of fitted values and residuals. So let's click run there. Okay, so this looks quite a bit better here when you're looking at this, in terms of, one, the fact that the residuals seem to be more or less, they seem to be a little bit more equal across the observations here. And the average residual error seems to be closer to 0 here. Now, this is by no means perfect, but we do see less of a departure from, we seem to address what might have been some issues related to nonlinearity when we were using that simple linear regression model. So if I thumb back here a few, you can see this is what our previous plot looked like with the same data using simple linear regression model. And so we do see an improvement here. Remember, we want the red line to fall on the dashed line here. Okay, so we're doing pretty well here. We seem to be in better shape than we were perhaps with using a simple linear regression model to fit these data. The polynomial regression model seems to be doing a little bit better of a job here. So the next thing that we're going to do is we're going to plot that normal QQ plot that we did before with simple linear regression. And so I'll just copy here. And we're just going to change the numeral 1 to a numeral 2 here to request the second plot. Click run. Okay, so this looks about the same as what we saw with the simple linear regression model. Remember, this plot is used to look at the assumption of whether the residuals are normally distributed. If they were normally distributed, they'd fall perfectly. These points would fall perfectly on this dashed line here. Let's click back here and take a look at, yeah, it's not much different. We looked pretty good in the first place. And so the residuals seem to be mostly normally distributed. So actually, I would say we are in better shape right now with the polynomial regression model than we were with the simple linear regression in terms of meeting statistical assumptions and fitting the data better. But let's take a look at now at the actual model results. So let's interpret the polynomial regression model results. Okay, and so just like we did before with the simple linear regression, we'll use the summary function from base R, type in the name of our regression model object, which is reg.all_poly, and we will click run. And let's take a look at our output here. Okay, so it's going to look very similar. You get your model specified, information about the residuals here. Now the next thing is we are going to have the coefficients section here. This is our regression model. And I'm actually going to rerun this so that this doesn't get truncated onto the next line there, or get wrapped around to the next line rather. So let's click run. Okay, so that's better. So here's our coefficients. And so you'll see we have our intercept value. We have, this is our non-quadratic term. So this is just points to the first power here, which is going to, anything to the first power will be equal to itself without being to the first power. Or, well, it's implied that it's to the first power, in other words. So this would be equivalent in this case to our model up here. This term just points by itself. Okay. Now, the next term is what we're really interested in here. This is what we focus on in a polynomial regression model. We want to look at the highest order term here. So the one with the highest exponent. So here the exponent is 2 for squared or quadratic functional form. Here's what we're testing. And what we see here is the p-value is less than 0.05, which is our conventional two-tailed cutoff. So we would conclude that to a statistically significant extent, including this quadratic term seems to improve the fit of the model after considering the linear nature of the model itself. Okay, so this is telling us, this is really all that we look at here. This is just telling us, good, we're on the right track here. This polynomial regression model seems to fit the data, specifically when we have a quadratic term and there a squared term. Now, if this were non-significant here, you would just back up and say, okay, let's go back to the simple linear model because there doesn't appear to be any additional variance explained by addressing any potential curvature in the association. Okay, so the next thing that we will do is we'll come down to the model fit information. Here's our unadjusted R squared value, which is 0.96. If you remember before, it was 0.8. What was it? 0.871 for the unadjusted, and now we've gone up about 9% or so. So that's really good. So we've gone from the great to the excellent fitting range, and our adjusted R squared is not too far behind at about 0.958 or so. So you could say when we're looking at the unadjusted R squared value that about 96% of the variability in pay is explained by the predictors in this model here. Okay, and remember this time we have multiple predictors, and one of which is the squared term of the variable of interest here. Okay, so this is saying, hey, this seems to work pretty well here by modeling a nonlinear model here. And here's the F value or F statistic associated with the overall model and the P value here, which is less than 0.05. So we conclude that this model does fit significantly better than a model with no predictors here. Okay, so this seems to be, we're on the right track here. The polynomial regression seems to be the way to go given these specific data. So let's now visualize the polynomial regression model that we just estimated. And so this is going to be a little bit more involved here. And so bear with me here, as this is going to be a 5-step process. And it's going to require simulating a sequence of variables first, or sequence of observations. So for step 1, what we're going to do is we're going to create a vector. And to make this run well or smoothly, name this vector the same name as your predictor variable, which in our case is points with a capital P. And then we'll use the SEQ, or the sequence function from base R, and as the first function, or as the first argument in the sequence function, because what we're going to do with it is simulate a sequence of values within a specific range and a specific number of values within that range. And so the first thing we want to do is set, okay, what's the minimum value? Well, let's do min, which is another function from base R, so minimum. And then the name of our data frame, MP, followed by $, to say that the points variable, which is our predictor variable, belongs to this data frame here. So we're specifying here as our first argument that this is going to be our minimum. So our minimum in this sequence is going to be the minimum of the observed points value, which is our predictor variable. Okay, so that'll be the minimum. And then let's copy and paste this argument here and paste it below, because the next argument is just not the min, but the max, so the maximum value. So what's the upper limit to the sequence that we're going to simulate? Well, it's going to be the upper limit of the existing points value here, okay? And so if you were to look at the points, it would be the min value is going to be 300, the max is going to be 999, okay? So we're just going to be, essentially what we're doing is we're creating values that we can plug into the plot. Okay, so the third argument is going to be the length. And so length, we just specify how many points in this sequence or how many values do we want to estimate or simulate. And I usually do 1,000 by default. You could do 100, doesn't really matter. It is going to happen almost instantaneously in terms of the estimation. So let's go ahead and highlight and run this. Okay, if you want to get a look at these 1,000 points, you can actually highlight and just click on points here, the name of the object, and you'll see we've estimated 1,000 points in this sequence here. So ranging from 300 all the way up to 999. Okay, so those are our 1,000 points. And so this is going to, then we'll later plug this into our prediction. We'll use it to predict and to create our regression line in a plot. Okay, so the second step, or step 2, is going to be actually converting this points vector object here to a data frame object. And so I'm going to call this new data, or rather new dat, not new data, because we'll actually be using an argument subsequently called new data. So new dat, all lowercase, use the left-handed arrow here to assign what is going to be a data frame object to this object called new dat. And we'll use the data.frame function from base R. And as a sole parenthetical argument, we'll enter the points vector. So remember, this is the points vector we just created here. We're just converting this to a data frame and relabeling it new dat. Okay, so let's go ahead and run that. If you were to click on this, and here you can actually see it pops up here in our global environment. You could click on it. So it's just a data frame with a single column here. We've just converted the vector to a data frame object. No big deal. All right, so the next thing is step 3. And for step 3, we're going to actually create our predicted values based on, by plugging in these values here, which from our points, which we then converted into a data frame object, we're going to plug these points values into our polynomial regression model to get predicted values, or fitted values in other words, okay? Because we're going to use these to populate our plot here in a bit. So let's create a new object. Let's call it predicted values. So predicted underscore values, all lowercase, is, you can call it whatever you want, but that's what I'm going to call it here. And we'll use to the right of the left-handed arrow, we're going to enter the name of the predict function from base R, which you can use to predict values from an existing model or a model that you've estimated. And so as the first argument, let's enter reg.all underscore poly to note that we're referencing the polynomial regression model that we've estimated here. As the second argument, we're going to enter new data equals and then new dat. So remember the name, we're saying this is the default argument name, and the predict function is new data. And to make things clear, I named this here new dat without an A, but this is the new data we're plugging in here. It's actually well, it's not existing data, but it's data that we've simulated here, which came from this sequence we created here. So we can plug it into our regression model. So it'll plug into this model right here with the intercept, the term to the first power, to the second power term, and we're plugging it in there to estimate predicted values, our y values in other words. Okay, so let's go ahead and highlight and run that. Now, if you want to, you can peek at the predicted values here, predicted underscore values object, this vector of values you've created. And you can see we will get 1,000 values. And these are the predicted outcome values. So these are actually in dollars. So this is the market pay that you would predict based on, let's say here was that new data or points value here. So 300, okay? So if someone had job evaluation points of 300, or a job had job evaluations of 300, if we come down here, we would expect them based on our model, that job to have a market value of $32,409.79. So these can ultimately be used as your midpoint in your model potentially, okay? Or if you're using this as a market pay line, which we'll do in a little bit here. Okay, so the next step is step 4. And for step 4, we are just going to plot the same plot that we did above here. So we're just going to come up here and actually steal this plot. So copy. So this is the same plot that we use for this is just the scatter plot that we use for the simple linear regression model. I'm going to paste it below here. Okay, so let's run that. Okay, so we get our plot right there. Okay, great, that looks familiar. What is the 5th step here? So step 5 is adding that polynomial regression curve. So it's not technically a line because there is curvature in it, but we do call it market pay line. So you could say a nonlinear market pay line, but technically it's a market pay curve here. And so what we are going to do is we're going to use the lines function from base R here. And as the first argument, type in the name of that points vector that we created above. So this is the points vector we created in step 1 here. So it's points with a capital P. As the second argument, we're going to type in the name of that vector that is our values, our predicted values. So this is the predicted values. So we're saying here's what's going to be our x-axis variable. Here's our y-axis variable. And then as our third argument, it's completely optional, I'm going to do call equals and then red to specify the color of this market pay curve that we're about to plot here. And I'm just going to make it red here. Okay, so let's add that line. Okay, here you go. So as you can see, this is a quadratic functional form. We've got a single bend in it, and it seems to fit the data better, at least visually speaking. And we saw the same thing. This was corroborated by the R-squared value, which was an indication of how well the model fits the data. So if you scroll back here to our simple linear regression model, where we just estimated a line here to fit the data, you could see that this seems to do a better job. And again, that's reflected by the R-squared values. Okay, so the next thing that you might want to do, or that you'll likely want to do, is to actually create the midpoints, which are just the predicted values based on this market pay line for each observed job evaluation point for each job that you have. Okay, so currently we have the market rates here. Okay, so this is what we got from our market surveys. So for the front desk receptionist job, if you have 300 points, $25,000 pay, well, we're going to create a new variable here that's going to be what would we expect based on our polynomial regression model here. And you would do this same process if you had a simple linear regression model too. Okay, so what we're going to do is we are going to create our predicted market pay. I'll put line, but we really mean curve values, okay? And so the first thing we need to do is specify the name of our data frame, which is MP, and then we're going to create a new name for this variable that's going to essentially be our midpoint variable for our market pay line here. And so let's just call it arbitrarily predicted with a capital P underscore pay with a capital P. And we'll use the left-handed arrow here to name this new variable or to assign values to this new variable here. And then we're going to use that predict function again that we just used a moment ago from base R. And this time, however, we're going to, as the first argument, we're going to do reg all underscore poly, which is the name of our polynomial regression model. As our second argument, we're going to enter new data as the argument new data equals and the name of our existing data frame, so MP. So it's just going to plug in to our regression model here the existing predictor values, which is points here, and in order to predict based on our regression model here what our y is or our outcome is going to be, which in this case is our predicted pay. And so essentially it's just going around on certain points on this line here that we visualize, it's going to estimate the values there as our predicted values. So let's go ahead and run that. Let's peek at our data frame object. Now we have a new variable here, which is predicted pay. And so here's what we would predict based on the model that we've estimated for the predicted pay or the midpoint of pay for the front desk receptionist here, okay? Because remember, this pay represents, let's say, the median pay that we gathered from or the average median pay that we gathered from across all of the market surveys and sources and so forth, okay? So for front desk receptionists, what we observed in the market actually is 25,000, but what we predict based on our model is 32,409 and 79 cents. And you see this reflected here. So here is 25,000 here for this case with 300 points, and then slightly higher is the actual predicted value, okay? And so it goes through and provides all these estimates here, which you can see there. Okay, so the next final step in all of this, and I know this is a very involved tutorial here, but this is how we would typically unfold this with real data, is, and I'll note that this is optional, we are going to estimate the minimum and maximum predicted pay. And this is a way of reflecting the range spread. So let's say that you want to create a range spread between the lowest possible pay and the highest possible pay for a given job or job family or classification. And so in this case, we're using job evaluation points, but you could have used, not as ideal, but you could have used you could have used grades here, different job grades, as long as they're numeric. That could have been used here as well. But perhaps we want to set kind of upper or ceilings and floors for how much someone could be paid within each range. And so let's say we want to apply a consistent range spread here. And this is completely arbitrary and just for the sake of explanation, but let's say we're going to set our range spread at 40%, which would mean that the maximum pay would be 40% more than the minimum pay at each level here, okay? Each level of the job evaluation points. Okay, so how do we do that? Well, we're going to use some basic arithmetic here to estimate. So the first thing we need to do is create a new variable. So we're going to add first the minimum pay variable. So we'll just note that we have our MP data frame, and we're going to attach to it a new variable we're about to create, which we'll call min_pay with a capital M and a capital P. Use the left-handed arrow to assign the values to that. And here's where the basic arithmetic comes in. We're going to do MP, the name of our data frame, $, and then that predicted pay variable we just created that we added here. Okay, we're going to take that first, and we are going to divide it using the / by, and note that I put parentheses here, 1 plus our range spread. So the proportional, what is equal to 40% is the proportion of 0.40 here, divided by 2. Okay, we're just splitting it here. Okay, so our predicted pay values divided by 1 plus our range spread divided by 2. So let's click run here. Take a look here, and now we have our min pay here. So this is kind of the floor here that we're setting for our market pay line. Okay, the next thing we're going to do is we're going to create a new variable called the max pay. So max pay with a capital M, capital P. Use the left-handed arrow again to assign values to this new variable we're creating. And this time we're going to use name of our data frame, but the name of the min pay variable we just created. Okay, and we're going to take that and multiply that min pay by, and put this in parentheses here, 1 plus 0.40, which will say that the max is going to be 40% more than the min. Okay, so min pay times the sum of 1 plus 0.40. So let's go ahead and click run there. And now you'll see that we have another new variable here, and this is the max pay. So you can see that the predicted pay is going to come in the middle of the min pay and the max pay here. Okay, and you can see we have this scrolled all over. Now you'll note that these are not going to be equal across these. The size or the width is not going to be equal because it's affected by what the predicted pay was in the first place. Okay, and so you're going to see that these intervals actually get wider between the minimum and max pay as you go up in job evaluation points here. So another thing that you might wish to do with this is to visualize the min and the max pay in relation to your market pay line here. So we're going to add two curves here that are going to represent the minimum and the max pay. And so to do that, you don't actually need to do it this way. You don't need to recopy this, but I'm going to do this because it's going to make this a little bit more clear here. I'm just going to go up to what we did before, which is where we had this 5 steps here. Copy. So I just copy those 5 steps from this plot we created above, paste it here. And I'm just going to add a 6th step here. And the 6th step is going to have 2 different functions that we're going to run. The first is going to be using that lines function. We're going to first specify as the first argument MP and points. Okay, so this is our this is setting what our predictor variable is essentially. And then our second argument is going to be MP $, and min underscore pay, which we created. So that's the first. Let's copy that. That's the first function. The second function is just going to be the same thing, except it's max pay here. Okay. So watch what happens when we run all 5 steps again here. Okay, now we have, and here you can see the range spread of 40% reflected, and here's where you can see those intervals are not equal. They actually grow as you go up. But you'll see that the black curves rather represent the min and the max, and the red curve represents that market pay line or the market pay curve here. Okay, so this can be, now all this can serve as the basis for creating your pay policy line, for creating subsequent pay grades, or whatever you plan to do with this. But this is how you build a market pay line here. Okay, and this is a situation in which I intentionally simulated data where we could estimate a polynomial regression model with a significant quadratic term in it so that we could see what you would actually do if you had an exponential growth here with respect to job evaluation points in relation to market pay. Now, in many cases, a simple linear regression model will suffice, okay? But in this tutorial, we covered both here. And again, you have all sorts of decisions to make, whether or not you really would estimate this market pay line for all job families in your organization, or you drill down to specific job families, specific geographic locations. Whatever the case might be, you really need to think carefully about this, and it really should reflect your organization's and your HR department's underlying pay philosophy and pay policies that you already have set in place, as well as the objectives that you have too, and any kind of strategic objectives regarding retention, promotion, and so forth. How do you incentivize people? For instance, this type of functional form here might be really motivating for people when they're at the higher end of the job evaluation points, because each additional job that they perhaps get promoted to or additional pay grade they move to, they'll see a notably higher pay increase than people who are down here, okay, in the lower levels, jobs that are seen as being worth less to the organization as indicated by their compensable factors through a job evaluation and ultimately their job evaluation points. All right, so this wraps up the tutorial on how you estimate a market pay line or a market pay curve if you're using polynomial regression in R. Thank you.